for joining this rendition of the KITP NSBP Innovate seminar. I'm going to introduce our speaker for today. His name is Dr. James Daniel Whitfield. So Dr. James Daniel Whitfield is an associate professor of physics and astronomy at Dartmouth College, where he investigates the abilities and limitations of new and existing computers for physical simulation. A graduate of Morehouse College with a BS in mathematics and chemistry and Harvard University, where he got his PhD in chemical physics, his research is supported by federal agencies and industry partnerships. He bridges academia and industry as an Amazon visiting academic and serves on the advisory boards for the IBM HBCU Quantum Center and the Coding School's Qubit by Qubit, reflecting his deep commitment to building an inclusive quantum workforce. His talk today will be called Probability First Quantum, Foundations, Fermions, and Understanding Quantum Technology. At the end of his talk, Carlton will be around for selecting questions from the chat. So again, the title is Probability First Quantum, Foundations, Fermions, and Understanding Quantum Technology. So quantum technology is advancing rapidly, but an intuitive understanding of its foundations remains elusive. This talk introduces a probability-first framework that reframes quantum theory as a natural extension of probability. And Dr. Whitfield will show how this perspective clarifies core concepts, guides the design of fermionic simulation methods, and helps define benchmarks for practical quantum advantage. So take it away, Dr. Whitfield.
All right, thank you for that wonderful introduction. I'm really excited to be here. Thank you so much for the invitation. This is really exciting. I've been to NSBP conferences, and it's really nice to be here as a chance to present inside this series. So today I'm going to talk about this idea that I've thought about for many years called probability first approach to quantum mechanics. And what I'll try to do today is give many examples of how we can use this to understand what's going on inside the current quantum zeitgeist in terms of what's going on and what's really exciting. Yeah, so quantum mechanics is this interesting theory people have been thinking about for many, many years, almost 100 years, over 100 years, in fact. And for me, this is something that came up as a very interesting area to start thinking about, it, very interesting area to work for a lot of reasons that have to do with quantum information. I'll talk about some of the research that my group does, but what I want to talk about today was really how we think about quantum mechanics and how I have come to understand quantum mechanics and how I hope I can help everyone else understand quantum mechanics. And then along the way, I'll also try and highlight some of the work that we've done inside of our research group relating to this idea from this perspective, in particular, some of the work that we've done on electronic structure. So I thought as a way to kind of set the frame for what's going on here, I'd start thinking about why do we even discuss the foundations of quantum mechanics? I did my postdoc in Vienna, where I was at the University of Vienna, and I spent several years there. There were many people in Europe who work on the theory of quantum mechanics, who think a lot about the philosophy of quantum mechanics, about whether or not quantum theory is the correct theory or not. And you can really see that this goes back to the history of science, back to the founders of quantum mechanics, where Erwin Schrödinger, who I have a picture of, who's a famous Austrian scientist, was upfront to say he was no friend of probability theory, which is quite a surprising thing to read from a scientist. Albert Einstein very famously said God does not throw dice. And Niels Bohr said that anyone who's not shocked by quantum theory could not have understood it. And I would like to try and emphasize that perhaps these are maybe old ideas that we can replace with new thinking. And that's really where the crux of this idea comes in. A lot of these ideas go back to even Feynman's suggestion to just shut up and calculate, which is very much the American US approach to thinking about quantum mechanics, where it's just, what can we do with these ideas? However, by going through this traditional approach of classical mechanics, the hydrogen atom, classical mechanics, and all these ideas that are very sensible from the point of view of physics, does not make a good entry point for other people interested in quantum computing or quantum theory for other reasons. And so this idea of approaching it from the probability first helps us think about this new technology with new explanations. And in fact, the explanations are in fact somewhat older, because probability theory is a very old idea. And so what I wanted to get in today was this idea of probability first, and this will take up the first half of the talk, more or less. I'll talk about some ideas around quantum computing, and that'll give us some focus, and then I'll end with some discussion of fermion simulations and some of the work that my group has coming out in the near future. So I think is the place that I like to start thinking about quantum theory is probability theory. And so when I think about probability theory, I think about probability theory formulated where I have a vector of numbers, and these vectors of numbers, the numbers inside that vector add up to 1. Those numbers have to be real, and they have to be greater than 0. And this is a very intuitive place for a lot of people to start, whether coming from statistics, psychology, or physics, where you already have a very good understanding of how probability and vectors work. And so this idea really helps us reach out to a wider audience of people, a wider framework to start thinking about how do we discuss quantum mechanics. I think one of the reasons that this came to me as such an important thing was not because I was studying the theory of quantum mechanics or the foundation of quantum mechanics, but rather because I had to teach it. And so in teaching quantum mechanics, I had to teach it to many different people, many different backgrounds, many different understanding levels. And all people that I've encountered in most fields have some notion of probability theory, as simple as, perhaps what the weather is tomorrow, whether it's snow, whether it's rain, whether it's overcast. And this is an example of probability vector where there's 25% chance of rain tomorrow. This idea goes to physical systems where you think about what's the probability that the system decided one particular state or the other, where it might be the ground state, the first excited state, the second excited state, or the third. And these are just probabilities, again, where this is just a probability of obtaining outcome upon measurement. So I'm going to summarize all these ideas of probability to say that a probability vector is a vector that has entries that sum up to 1. Each entry is greater than or equal to 0. And I'm also going to add this additional requirement that these probabilities are real. That may seem like a strange requirement, but it makes a lot of the mathematics nicer to generalize the quantum theory. So just to kind of say something about the kinematics of how we can think about probability theory from the point of view of physics, is that if we think about probability theory, we just start off with this idea that we need to maintain these constraints, these 3 constraints of normalization, reality, and of positivity. Then we can set up what are the allowed transformations of this probability vector. And perhaps the simplest transformation of probability vector is just rearranging the entries. That's permutation. That's where you have some set of events and you just relabel the events is an example of permutation. A Markov chain is where I do some sort of mixing process where I have some probability of going from a site K to site J, and that's some transition probability. And after I take whatever probability I was in, do some updating rule, and I end up with some final probability, which is here labeled with this F for final. There's all this notion of collapse. And so in quantum mechanics, a lot of the discussion around the turn of the century and so the first half of the century was really around this idea of collapse of the wave function. I would like to highlight here that this notion of collapse happens here with probability. So if I'm asking you, what is the weather tomorrow? And you say, well, 50% chance of rain, 25% chance of snow, and so on and so forth. When the weather occurs tomorrow where it does rain, then you have 100% probability that it will rain. And then all the other probabilities are 0. And so you can think of this collapse idea as a very simple notion inside of probability theory that almost comes for free. And we'll see many other examples of such throughout our talk. So how do we take this approach to think about quantum mechanics? Well, in quantum mechanics, we have matrices, and these matrices are now, you can think of them as probability density matrices. So just like a probability density vector, now we have probability density matrix. And this probability density matrix has on its diagonal probabilities and the off diagonal quantum coherences. These quantum coherences are what's really important about the system. And this is what we'll use most of our time talking about quantum technology and how these coherences play a role or don't play a role in understanding when and where we need to use quantum computation. So maybe a little more formally, This idea of the quantum probability density matrix is a matrix where we have the eigenvalues sum up to 1. The eigenvalues are real, and the eigenvalues are all greater than or equal to 0. And those align one-to-one with the conditions that we need for the probability vector, where the probability vector needs to be normalized. It needs to have real entries, and these entries need to be greater than or equal to 0. So this is exactly how I set up quantum mechanics as my classes, the way to kind of introduce quantum theory to various people from various backgrounds, whether it's a very highly technical background or something with some very introductory ideas of what a matrix is. In all cases, the idea is that this really gives us a framework to also understand what's going on in quantum technology as a way of thinking back to what is the analogous situation in terms of probability. And this is really how we start to think about what theorems we'd expect, what outcomes we'd expect, and how we really expect quantum theory to play out for us. So yeah, just reiterating, this idea of the probability density matrix is a matrix where the eigenvalues sum up to 1, the eigenvalues are greater than 0, and the eigenvalues are all real. With this interpretation, every time we look at the diagonal of this matrix, it is always a probability vector. And this probability vector allows us to do kinematic updates in the same way that we think about what are the allowed transformations that preserve these properties. We end up with 3 different properties that really map to the same exact idea that we had for probability, where we could do some unitary evolution, where this does not change the underlying eigenvalues, the underlying probability distribution, but rather just rearrange it. In the same way that we think of a permutation as not changing the entries of a probability vector, just relabeling where they are. And so you can really think of unitary evolution as very much just relabeling the state. The idea of quantum computation is that we're going to use these unitaries to relabel the state such that the final state is the answer, and then we measure the answer with high probability. This idea of unitary evolution, so where we just have some unitaries, which u times u dagger is equal to the identity. This dagger, just to be clear, is the conjugate transpose of the matrix, and not just the conjugate. This idea of a quantum channel is the idea that we don't have to apply just one unitary. We could apply more than one unitary with some probability. In the same exact way, we have a Markov chain that can allow us to change the probabilities, the probability entries of the probability vector, the same way this quantum channel allows us to change what are the eigenvalues, what are the probabilities, the intrinsic probabilities of this density matrix. And finally, this idea of measurement collapse is exactly the same as it is inside of probability theory, where when we measure and we get outcome J, then state is either projectively put into state J or we re-prepare the state. So we can think about this measurement collapse idea in the same exact way we think about the weather distribution of what's going to happen tomorrow, and then we find out the weather's warm, it's sunny, find out that it's rainy, it's cold, and then that really puts us back into one particular state. So I will pause here and check and see, are there any questions, or should I just wait till the end?
There are no questions, but yeah, we could just go forward.
Okay, great. So a few highlights on quantum information theory that I think are really important to put up front that you find inside the literature, because people did not start with probability first, is thinking about quantum computing as trying all the possibilities at once, or that quantum states have much larger state spaces than their classical counterparts. But I'd like to highlight that if we have a quantum state, that quantum state has some exponential number of entries, but so does the probability state. So if we have 3 bits, 3 classical bits that can be in the state either 0 or 1, so you can see the first entry is either 0 or the first entry is 1, the same thing for the second and third entries. And the idea is that because they can each be 0 or 1, I have an exponential number of points I need to describe the state that has 8 possibilities, 8 bits. And so this idea that quantum computers are trying all the possibilities at once is exactly the same idea as if we had a probability distribution that tries all the possibilities at once, and we really haven't gained anything. So whenever you hear that quantum computers are just trying all the possibilities at once, this is one thing I would like you not to take forward. So if we ask what then are quantum computers good for, it is using these off-diagonal elements in order to generate correlations. So this idea of correlations in terms of probability distributions are that we have two things that are uncorrelated if there's a way to separate and measure the outcome of system A independently of system B. However, when system A and system B have some correlations between them, there's no way to write them as a clean separable state. The same exact idea carries over to quantum correlations, where we still have the same notion of combining two smaller systems, and then we get a larger system. And that larger system will either be correlated or uncorrelated, depending whether or not it has some separable decomposition. The off-diagonal elements of the probability density matrix allows us to have stronger correlations. This is really what is at the heart of all the quantum technologies that people discuss, whether that's quantum communication, quantum computation, or quantum sensing. And we'll talk about all these things in turn. But the key idea I'd like you to keep in mind is that these quantum correlations, which are generated because of these coherences, are what's giving us the power of quantum computation. So again, this has consequences of data processing, data sharing, and it really allows us to lose a notion of the states individually. This has a lot of philosophical consequences, which are all interesting, but really you can think about it as saying that if I want to describe what's happening with subsystem A, then I need to have subsystem B, because B contains information about A. And without all the information about A, there's no way I can say what is that state exactly. It's the same exact idea of being correlated in the other way. I think one of the examples I like to give of how entanglement and how strong correlation are very much the same are the idea that if I took a stick and I paint one end of the stick red and the other end of the stick blue, and I break that stick in half and I give one half of that stick to you, and you go off to wherever you go, and then you look at your stick and you see that it's red, then you know immediately that I have the blue stick, and that's us being strongly correlated. But that doesn't violate anything about communication, fast and speed of light, doesn't have any consequences on the physics or the actual situations, just that you don't know the information until you look at the bottom. And as soon as you find out what color you had, you know immediately what color I had because we were strongly correlated. And the same idea can be used for data processing and for data protection. There's a lot of information here, and so maybe I'll just highlight just 2-3 points off of it. But the first point here is that this approach of probability first means that any interpretation of probability, whether it's frequentist, Bayesian, ontic, epistemic, ontological, all these different ideas, all are captured by this notion of quantum mechanics as an extension of probability theory. We just talked about entanglement and superposition. Superposition is not at all a quantum mechanical phenomenon, in that we can see superposition of any linear system, whether that's musical tones or waterways or any other vibrational system where we can have superposition of vibrations. So this idea of superposition is a quite general idea, and so is this Heisenberg uncertainty principle, where again, we have this notion of Fourier transform that is causing some uncertainty in one position or the momentum. In the case of probability theory, the Fourier transform of a probability function is a characteristic function, and it also contains the same information about the probability state as it did inside the direct picture. Okay, so all this to say is that, coming back to the original part of this talk, which is thinking about how do we understand some of these early debates that were going on inside of quantum mechanics, some of the early thought experiments. And I think this Bohr-Einstein debates are really at the crux of asking what is the meaning of quantum mechanics. Erwin Schrödinger put out this idea of Schrödinger's cat, and I find this example very not very informative, because if you took a cat and you flipped the coin, then you'd have the situation on the left where you decide one of these outcomes is the case that you're going to have the cat die or not. And the only difference between Schrödinger's cat and the ordinary flip a coin and hurt the cat is this idea that we have coherences on the off diagonal. So these coherences are really what separates this quantum cat from the ordinary cat. But in both situations, the probability of the outcomes are still the same if it's 50-50. And so this is one of the ways that I hope can help you wrap your head around some of these questions people are grappling with, which is rather than rejecting probability outright and say probability is not the way to think about things, instead starting from probability and building up our understanding from there. I would say that one other indication that this might be the right way to think about quantum mechanics comes from also the history of quantum mechanics, where we have Planck first discovering this notion of quantization in his study of thermodynamics, where we have a lot of these ideas of probability showing up quite naturally. The same thing for Boltzmann, where he's really thinking about the Boltzmann distribution and how temperature plays out. And a lot of these things are what allows us to understand the statistical and probabilistic nature of quantum theory. Okay, so maybe to kind of bring it down to a little more realistic situation, maybe we can think about flipping a coin. So this idea of flipping a coin and doing repeated flips of a coin is something that we call Bernoulli trial. This is anytime you have two outcomes and then some probability distribution for what happens at each outcome. And if we think rather than what's the weather tomorrow and what the probability distribution for tomorrow's weather is, we think about a coin that has some bias, then that bias of that coin may be, biased towards outcome 0 or biased towards outcome 1. And that idea of the bias is going to give us some directionality to what outcome we're going to expect to see. And so this red dot here inside this picture along this red line that represents our probability possibilities. If this red dot were at the top, then we flip this coin every time we get outcome 0. If we're at the bottom, then every time we get outcome 1. And where it's at right now with P equals 0.75 means that 3/4 of the time we get outcome 0. And then 1/4 of the time we should get outcome 1. And so this is the bias towards one outcome or the other. And this notion of bias really helps us think about what happens if you flip this coin repeatedly, how we expect to see the situation change as far as how many times we get 0, how many times we get 1, different interesting ideas about probability show up almost immediately, just thinking about the simple game of, how many times you got heads or how many times you got tails. Okay. So this idea gets generalized in the quantum case, this idea of a sphere, where now we have access to X, Y, and Z axes here. These X, Y, and Z axes allow us to move this red dot anywhere along the sphere. And then that red dot, if it's on the surface, is going to be a situation where I will get an outcome with 100% probability if I measure in that direction. And so the way you can think about this is that for every single direction of the sphere, there's an axis that will go through it. It's an axis that goes from psi through to the other pole out the other end of the sphere. And this axis through the Bloch sphere is a measurement axis. And we can ask, what is the bias along that measurement axis? And that measurement axis may or may not be aligned with where this red dot psi is. It could be aligned along the 0, 1 axis, and we can ask what's the measurement probability, and we just do the projection onto that Bernoulli line. And so this measurement in any axis is really the key difference between the quantum case and the classical case. And the fact that we can have it not be inside the 0 and 1 situation is due to the coherences that are allowed by quantum theory. Okay, so that was my introduction to quantum theory from the point of view of probability first. And now what I'd like to do is turn towards engineering with my remaining 15 or so minutes. So when we think about quantum technology, we're going to think about it from the probability first perspective. And well, I'm going to take 3 different cases to kind of talk about how this perspective helps us understand what's going on. So I'll talk about quantum computing and quantum sensors. I'll talk about quantum advantage benchmarks and some of the ideas there. And finally, I'll talk about error correction before saying a little bit about fermions. So the idea of quantum information carriers is that we have physical devices that will behave as if they were quantum mechanical, and we can maintain that coherence. Those coherences then allow us to access all these features of quantum mechanics, including entanglement or measuring inside of different directions inside the Bloch sphere, and all these different ideas that people are chasing down in order to think about quantum computation as a practical endeavor. So there's many different types of devices, superconducting devices where Josephson junctions are used to create qubits. There's atomic systems where either neutral or ionized atoms are used to have one or two levels isolated. To have two levels isolated. Those two levels form a qubit, and then there's different ways to couple those qubits. There's many different examples of qubits that are available now. Some of them have been commercialized, some of them have not. And it's really a very wide open question as to what the final type of qubit will be. Right now, many different types of qubits are in the race, and superconducting qubits are one of the more popular types. So how do we understand quantum technology in terms of this discussion we just had? So I would start by saying first, all these quantum systems are going to be described by a quantum probability density matrix. So anytime I have a superconducting device or a ytterbium-based ion trap, when I measure that device, I will be getting out something according to the outcomes of the probability density matrix. This idea of quantum technologies are the devices, communications, and detectors that rely on quantum coherence in some fundamental way. And so when we think about the difference between a quantum computing device and a quantum sensing device, it's really two key differences. So for a quantum computing device, there's the so-called DiVincenzo criteria, which lays out 5 different criteria you need to have a quantum device. And they essentially boil down to these 3 main things, which are that you need to be able to initialize your quantum device, you need to be able to control the dynamics, whether that's through quantum gates or through some other control mechanism. You need to be able to read out the information when you're finished doing your computation. On the other hand, if you don't have a good qubit and your qubit's noisy, well, this often makes for good sensors. So if you have a qubit where you can read out the information, reading out that information when the qubit is not well under your control means that it's under control of the environment. And that really allows you to learn something about the local environment of that qubit or about what's going on inside the system. And so examples of that would be like magnetometers that are built using superconducting, built using NV centers. So quantum computing today, I think a lot of people who step away from quantum computing are quite often surprised to find out that you have access to quantum devices today. There are actually 5 devices available on Amazon Broadcat, with Alpine Quantum Computing just coming on onto the device about a week ago. Amazon Web Services is the most comprehensive and broadly adopted cloud platform. And among those services that you can use to provision devices to have scalable computing on demand is Amazon Broadcat, which can be integrated into any other workload. Now, let me see. I believe there's a question. Yes, so in the question, there's a question here about using more than 2 or more basis states. So yes, it is certainly reasonable to build quantum devices that use higher level. And quite often what happens is that the higher level excitations are used for doing 2 qubit gates. It turns out that there's no formal reason for going to 3 levels. However, quite often in practice, it can be useful. Hopefully that helps. Great. Yeah, so many different types of devices that are all available. Then what people are doing in the industry now are really thinking about how do we convince ourselves that quantum computers are doing something interesting? How do we convince ourselves that we have a quantum device that's doing something interesting, that there's something that we can say? And so there's a lot of protocols for thinking about how do we argue for quantum advantage, and all the arguments of quantum advantage really come down to this idea of sampling, thinking about how do we actually make statistical arguments about what we're measuring to say that there's no other way we could have made this probability distribution. And the idea is that we're going to randomly implement some circuit, some unitary circuit, and the idea is that if I have a very good quantum computer, then I can do the dynamics. I can control the dynamics of the system. I can evolve this probability density matrix to some final state and then sample from it. And that will allow me to make arguments about whether or not my quantum device is doing something you could not have done any other way. So again, the initialization, the control of the system, and the readout of the system are the 3 main parts that people are trying to build at Google, at Quantinium, at AWS, and many other companies. From the point of view of the probability first, there's also many problems that arise almost immediately, which are first thinking that this idea of quantum primacy relies on some way of validating that you've done the problem correctly. Unfortunately, for comparing probability distributions, there's not a lot of ways that you can compare them. So if I have a probability distribution and you have some probability distribution, other than us doing measurements over all the possibilities, which we already highlighted, are exponential in the number of bits, means that there's no way that we can find out if our probability distributions are the same without doing many, many samples. And so you come up with other ways of trying to make estimates of whether or not you've reached your goal that don't require an exponential amount of sampling. One of the benchmarks that people have proposed and been thinking about for many years now is this linear cross entropy. But this linear cross entropy is a statistical measure, and one of the main problems about making this argument, making the argument rigorously, is the ability to spoof that score. So statistical proofing. This is an example from last year where some authors were thinking about how to spoof the system. So rather than actually trying to build a quantum device and do the quantum circuit and do the full evolution, rather some way of cheating the measurement of the outcome. And so you can think that I can put all the noise inside of the low probability states, and that way I can get something that's very close to the right answer, but for all the wrong reasons. And so this is in opposition to this idea of actually doing the simulation, where a lot of the effort that's been put into refuting quantum supremacy claims have been about building bigger and faster tensor network contraction schemes, different ways of mimicking quantum devices. These same notions of mimicking quantum devices, the tensor network simulations, have also been applied to probability in many different instances, as well as multilinear algebra. And so the crux of this question is really, what is the difference between quantum and probability theory? Right, and for another example is part of the current zeitgeist of what everyone's really thinking about and what a lot of the work is going into is thinking about quantum error correction. In quantum error correction, this is again building off of probabilistic theories of coding theory, which is how much I can compress information, whether it's MP3 or JPEGs, and information theory, thinking about transmission over noisy lines. This is where you have something like Wi-Fi, and you're trying to make sure you're not dropping too many packets when you're at the edge of reception. And here's an example of a quantum error correcting code. And I just put in a picture of an elephant because I thought elephants cool. They memorize a lot of things. And I thought it also was very indicative of what's happening inside of quantum computing, because in quantum computing, in order to have one single qubit protected, you need many, 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 many qubits. And so the quantum devices, just for having one or two qubits, end up looking more like elephants than, than cheetahs. Okay, so I'm going to go to my last section here and try and end at 45 minutes. So I'm sorry I didn't tech this up. A little embarrassing, but we'll just roll with it. This idea of fermionic simulations is something that my group works on a lot. One of the key ways I'd like to highlight how to think about fermionic systems is thinking about two different types of distributions. So the normal probability distribution, which is quadratic in your variables. You have some distribution that has very nice properties in terms of its Fourier transforms, in terms of its higher order moments, all being products of the first and second moment. And what happens, we go to quantum mechanics for these free fermion states. Here, these alphas are fermionic operators, but all the main ideas of Gaussian properties carry over to these fermionic Gaussian states. And so this Gaussianity is really a dividing line that really helps us think about the dividing line between easy and hard problems when we think about this in terms of quantum computing. And so our group really works on this boundary of thinking about particles with no interactions and particles with interactions, and what happens on that boundary and how we can understand and push the boundary one direction or the other. And so this comes to this idea of how do we build crash tests inside of a quantum device, where we want to mimic what really happened inside of some collision. Rather than actually doing the collision, we want some cartoon version of it. And the idea is that we want to take our molecular system, figure out some differential equation that governs it, and then either solve that on classical computers or solve it with quantum simulation. And this is really what our group has been working on. We have a lot of different ideas about fermionic qubit mapping. There is a Nature reviews that will be coming out early next year, where we discuss all the different ways of encoding this fermionic situation into qubits. So the idea is that we need to have some algebra for the fermions that needs to map to the algebra for the spin systems. And there's many different ways to do it, starting from 1920s. So very much inside the vein of this talk, this is very old ideas that have been supplanted by many other ideas, ancilla-free encodings, higher dimensional geometric localities, symmetry-based reductions, and then many of these ideas come into different ways of considering what we have to do in order to select the correct fermion encoding. And this is really where our group has done quite a bit of work. And so with that, I'd like to just kind of highlight the key points of this talk. Is that quantum information science is a study and application. The summary for this talk, the probability first approach to quantum mechanics uses probability as a conceptual and mathematical foundation for understanding. The quantum technology to detectors, devices, and communication systems rely on quantum resources, and quantum theory is an extension of probability theory that's relevant whenever quantum coherences are present. My group consists of several PhD students and undergraduates, this work has been done by several generations of PhD students working inside my group. And I wanted to really stop here and thank the National Society of Black Physicists for the invitation to come present today. And I hope that we have questions from the audience.
Thank you, Dr. Whitfield, for the great talk. As somebody who does statistical physics and stochastic processes, this was a great way of actually getting an intuition for quantum mechanics and quantum information. So I'm a fan of the probability first approach.
Great.
I want to emphasize again, if you have for the audience, if you have any questions, feel free to use the Q&A feature below. But I guess I had a question. You had the plot with the bosons, fermions, with interactions, without interactions. Are the fermionic like simulations easier because of something like the exclusion principle, and bosons are harder because you can have a combinatorially like more ground states than you can with fermions? Is that
So no, I would say it's a little bit different, but that's a very good intuition. I would say maybe the way you should think about it is that for bosons and fermions, there's this notion of normal distributions, Gaussians. And so for fermions, the Gaussian's really nice. It has a lot of really nice properties, but the Gaussian's directly connected to the determinant. The determinant has beautiful mathematical properties. I don't know what happened, but God must have just smiled upon mathematicians that day and said, we're going to take this combinatorial formula for the determinant and make it equal to the eigenvalues, the product of the eigenvalues. And that is something very special that only happens for fermions, does not happen for bosons or for other types of particles. And that connection to the determinant is really what allows you to get away with very easy computation.
awesome? Thank you.
Let's see.
So I guess the first question is from an anonymous attendee. They wanted to say that the probability first perspective is very thought-provoking and contradicts a lot of their training as physicists. They wanted to ask if there's an article or a place that I guess rebuts the probability like first approach.
Yes,
Or
I have.
are there places they could read more about the probability first approach?
Yes, I have an older paper that I can suggest. I do hope to have some material posted, some newer material posted that would kind of highlight some questions that people can look at, some ideas about how this might be implemented inside of class. And so I think there's also a question here. Okay, well, I'll return to that point in a moment, but maybe I'll address these in order. So, hey, Thomas. Hi, Thomas. Okay, general questions. Yeah. I guess general advice, I think one of the general pieces of advice is maybe just to think, one of the things that I've heard a lot, and I have to counsel my students, and undergraduate and graduate students and postdocs as well, is really thinking about what's going to happen inside the future. You know, a lot of people are very concerned about jobs, concerned about AI and jobs, concerned about whether they'll get into grad school, whether they want to stay in grad school, whether there's going to be positions afterwards. And one of the things I like to remind people and like to kind of underline to everyone who's out there thinking about science is remember there'll always be a place for smart kids to get together and to find their niche, to really think deeply about interesting things and really to go deep. And so I would say, you know, for me, and I think even Kanav, who's mentioned inside of there, and I assume also Professor Searles, is really this idea of a love for science. If you love science, then you're doing it, and you'll find the people who also love science, and you'll do it with them. And it won't really matter if AIs are involved or not involved, if people are going to pay you lucratively, if they're going to pay you okay. Because when you really find that community, that's a community that's going to support you in being a scientist, and that's a really good time for you to just remember, enjoy it, do your best work, do as much work as you can. So,
Thank you.
okay. This question is also really nice. The paper that I posted a few minutes ago, that paper is really kind of the first outlines of the idea. And so in my undergraduate courses, I've really taken a lot of time to bring this probability first approach to really think about how do we actually present things. So I'm in a physics department. And so our undergraduate curriculum is set up to follow quantum mechanics from a physics point of view. However, when I teach graduate courses, which is actually where I think this approach is much more relevant, is in a graduate context where you're going to get people from many different fields. You get people come from engineering, from mathematics, from aerospace engineering, wherever they're coming from, and they're going to have all these different ideas about whatever they have. They have a technical background, and this is a great place to start the conversation. I think if you're building a technical background, you might not start here because, well, there's going to be a lot of things you have to learn about atomic physics, about nuclear physics, about how to apply all these ideas. Or if you're coming from biology, you have to learn biology. And then you come to quantum mechanics and you ask, hey, how does quantum theory work? Well, all that probability you learned in biology, all the probability you learned in engineering, wherever you learned it from, we can start that conversation over anew. And so that's really where it shows up. So it really shows up at the tail end of the undergraduate curriculum for all the undergraduates coming out of any sort of mathematical training at all. So we get a lot of computer scientists showing up, a lot of engineers, people from across the campus show up to take the physics quantum information course.
Awesome. I think this is currently all the questions from the audience. I did have.
Carlson, I had a question if you don't mind.
Yes.
Sorry.
Alan yeah.
Yeah, I didn't see the questions coming in from the chat, but I wanted to ask Professor Whitfield if maybe you could touch on the idea of academia intersecting with the private sector in quantum. I know that you mentioned Amazon and you're involved with them, but also I think correct me if I'm wrong, you were at the start of QBraid as well, so maybe you could speak to that. And are those positions like increasing in the future?
Yeah, it's a great question. I don't have the crystal ball or anything like that. I will say, the job market is what it is, and I don't mean that in any sort of like dismissive way to answer that question. But I think your training as a scientist also is whatever it's going to be, and whether you enjoy doing science or don't enjoy doing science is really a question, right? So if you're doing science as a means to an end to be able to get a good job and to support your family, okay, then I think that's a very different off ramp for what you're going to do in terms of how far you might go to study. Well, if you want to go to the quantum industry and get to work today, go get a master's degree in a year, 2 years, and you'll be set up to go to industry, to be able to apply to jobs, have a strong CV, strong resume, to be able to find a job in this market. If you're going in to do your PhD, go there to do your PhD and relax, put your head down, and don't say that relax and be oblivious, But whatever the job market is now is not what it'll be 4 or 5 years from now. Like we have no idea what it'll be 5 years from now. So the best thing you can do to prepare for the job market 5 years from now is learn everything you're supposed to know. Everything you're supposed to know, whether that is, thermodynamics or it's quantum mechanics. You need to learn all the main things you're supposed to know in order to be prepared for whatever the job market is when you leave. I had no idea quantum computing would be an industrial activity when I was doing my PhD. I thought error correction was a joke. I mean, the number of qubits you need in order to stabilize one quantum qubit is actually a very large number, and I thought they were joking. But it turns out no, people are really building this now, and that's years later. And I was here because I was enjoying it, and now it's still here, regardless of whether I enjoyed it or not. And so the advice I give is to go down, follow your passions, and put your head down and do your best work, and then you'll find a job. I think that's the way I think about it. I mean, not to say that's the only way to think about it, of course.
Thanks for that insight.
Yeah.
Professor Nardi, is there any more in the chat?
Yeah, there's a really nice question here about match gate circuits and René stabilizer entropy. This is actually really fantastic because we're doing this now. This is actually one of the things we're coding up. So one of the projects we have going on now is coding up a library that just allows us to do free fermion physics. It's the free fermion library, and this idea is that you can use stabilizer René entropy, but also there's an idea of fermion anti-flatness, another criteria for thinking about non-normality of a match gate circuit and what the output is. And so that's a little more technical, but it's really thinking about how do we know if a match gate, if the output of a match gate circuit is, well, actually, the output of a circuit is consistent with the being outgate of a match gate circuit. And so how do we distinguish the fermionic aspects of one state from the other is really at the crux of this question. But I think it's a fantastic question. For sure, feel free to reach out. We'd be really interested in hearing what your thoughts are and questions. Some of my graduate students, Andrew Pajansky and Jason Nicase, are working on this problem now as we speak. So,
Awesome. I think this is all of the time we have for questions. I guess want to extend our gratitude to Dr. Whitfield for taking time out of his day to deliver this lecture and for answering these questions really thoughtfully. Yeah, I guess to the audience, we hope to see you at the next Innovate seminar to be announced.
thank you.
Yes, thank you.